Okay, so let's get started. Before we dive into the lecture, two announcements. One you've already heard. So remember, for the exam, which is tomorrow evening, we're gonna split into two groups. So there's the algorithm right there. 15, 17, 18, and 19. If you're one of those labs, you go to 10 Evans. Otherwise, 1 Pimentel. And if you need any special arrangement, talk to Brian, who is, as you know, sitting right up in front here. Okay? And then, I don't know, Dan, is there any announcement we need to make on what? Oh, okay, I can read that. If you can't find our webcasts on YouTube, try iTunes U. Sometimes there are video glitches, and YouTube won't take audio-only podcasts, okay? And then what do we do here? 3? 3. Okay, so, all right. So just in the news, this is, again, I'm cheating a little bit because this was last month, but it's relevant. Google took the unprecedented step of detailing the energy usage of their data centers. And what they disclosed, this was early September, that basically they're continuously using the amount of energy it would take to power 200,000 homes, which is, you know, a pretty decent-sized city. You know, you might think that that's a bad thing, but part of the argument that they made is that actually it makes the planet greener than if people were getting in their cars and going to the library and doing all this. So you can do that evaluation for yourself. You know, what's your part of that? Basically, per day, each person that uses Google basically burns a 60-watt bulb for 3 hours. That's about how much energy gets used. So that article's in the New York Times. The other reason I put it up today is because the person interviewed in that article is Urs Hosel, who's one of the main data center guys at Google. He's also the co-author of the reading that was attached to today's lecture. So he and one of the other leading data center guys there put together this free book that describes warehouse-scale computing in data centers. And we're reading a couple chapters from that. So again, since, let me just grab the door here. Since this isn't on the exam, I don't expect anyone's looked at that yet, but it's an easy read, it's a good read, and when you're recovering from the exam, I recommend you click on the link. It's a free book. Okay, good. So I believe it's lecture 17, and the topic is data centers and cloud computing. So what I want to do today is not stretch your brains too much and not stress you out too much. So, here's where we are in the class. These are the 6 big ideas that we're, trying to hit over the course of the semester. We spent a bunch of time talking about representation and interpretation, right? So the different layers as you go from, C language down to, various types of assembly language down to the machine code. And we had a nice lecture last time on how that all gets turned into a runnable program through the process of compilation, assembly, linking, and loading. So we've been talking about that quite a bit. We also, if you remember, which hopefully you do because it'll be on the exam, we talked a lot about cache hierarchies and locality and why cache hierarchies work. So we've kind of hit that one. In the process of talking about caches, we did a little bit of performance measurement. So we'll go back to that later. But we've talked a little bit about how to measure and improve performance. And so today is really the introduction to one of the other big ideas, and really one that we are emphasizing more this semester than we have in the past, and that's the idea of parallelism. Okay, so we've seen this already in a couple places. We talked a little bit about how the cycles per instruction can actually be less than 1, so that if you do things at the same time, multiple things at the same time, you can actually be running instructions faster than an instruction per cycle. So we've seen it there. When we looked at the picture of, it was the Nehalem processor, we saw that there were 4 cores there. So that's 4 processors that are all going to be running in parallel, so we've seen it there. We're going to go back to that later. But what we're going to talk about today is kind of thinking about that problem blown up. Okay, so thinking about that problem at sort of its largest scale, which is the idea of, it's not that, it's the idea of warehouse scale computers. Okay, so little history. This is what computers used to look like, and actually they look a lot like this again, which is kind of funny. But that was your CPU. This is all I/O stuff, whether it's tapes or card readers and things like that. This is in the 50s and 60s. There's actually two people in that picture, which is actually important for our discussion today. Although they don't warrant any mention here. So they're neither part of the CPU nor the I/O. I guess they're more part of the I/O system. So, but the idea is big computer filled a room. A big breakthrough there was the idea of time sharing, so you could have multiple things going on, sharing those resources at the same time because they were expensive. And also, those I/O systems were really slow, and so while you were waiting for things to come in, from your tape, say, or even from, where the disks are over here. Oh, no, those are printers. Disks are over here. While you're waiting for those to come in, you could be doing other things using the processor and so on, okay? So that's that. Roll the clock forward, a decade or two. There's this idea of mini computers. You don't really have the scale here, but this is kind of the size of a big refrigerator, right? So if you're into fancy kitchens, this is maybe the size of a Sub-Zero, or two Frigidaires next to each other. And the idea here was, much lower cost. Instead of $1 million, it was measured in the 10,000s or tens of thousands of dollars, and it was meant for a department or for a university lab or something like that. These are called mini computers. This is a picture of the VAX 11780, a machine that Dan, even though he won't admit it, knows very well. Then roll the clock forward, PC era. This is one of the early PCs, the IBM PC, which is the one that really broke open the market. Again, another order of magnitude decrease in cost, so you could get these in $1,000 range, and it was meant for a single person, right? And that was a big breakthrough, right? So the idea that you as a person would have a computer all to yourself was a crazy idea because computers were so expensive, right? That's why we're doing all that time sharing and all that stuff on those big mainframes. So, at the end of the last century, this was kind of what people thought was going to happen, is that everybody would have their own computer, and that's where all the computation would get done. Okay, well, where we are now, as I think we talked about in the very first lecture, is this idea of a post-PC era. So what's happening is the computing world is kind of splitting into two very kind of the polar opposites. Okay, so on one hand, you have these personal devices, like your smartphone, that are on order of hundreds of dollars, and can run applications, can communicate, can do all the things that you like to do on your smartphone, right? Have sensors and so on. So these personal mobile devices, that's at one extreme. And the other extreme, we're almost back to that first picture I showed you, that big mainframe picture, where there are these huge clusters of shared resources, right? And again, the price goes back up to millions or even hundreds of tens or hundreds of millions of dollars to build these things out. Okay. So what happened over the last few years is the middle ground is sort of starting to give way. And you're ending up with really, really, really personal machines that you can carry in your pocket, and then back to the old mainframe approach where there's a bunch of shared resources that are available across, by going across the network. Okay? And so we're not going to talk too much about this guy for a while, although later in the class we'll talk about what's inside the iPhone and systems like that, and we'll look at those processors. Because what's in there looks a lot like the MIPS. I think it is a descendant of the MIPS, actually. Dual-core MIPS. And what we're going to talk about today and for the next couple lectures are these guys, right? The bigger side, the big mainframe side of the picture. Okay? All right, so, there's a lot of excitement about cloud computing. I just, this morning, had to give a talk to an industry group about cloud computing and what that's about. Before that, I had a guy who, I forget his title, but it was assistant deputy something, but he had the White House as the address on his business card. and he wanted to talk about cloud computing. I mean, the stuff, everyone wants to talk about cloud computing. So, why is everyone so excited about cloud computing? Well, part of the reason is it's sort of become possible, okay? So you can build out, because there are these big shared services that people want to offer, it makes sense to sort of build out a big infrastructure where you can host one of those things, okay? And not to have necessarily every company doing it on their own. So some companies, like we saw with Google early on, at the very beginning, they do run their own data centers. And if you go to Google's webpage and poke around, they'll actually show you a list of at least some of their data centers and where they are and a little bit about how big they are. Okay, but once you get down from sort of the top, few dozen big companies in the world, it starts getting very expensive to run a big data center. And so the idea was maybe we could concentrate some of these resources and then make them available as a service or as a utility. Okay, so and there's a bunch of advantages to that. A big advantage, and the reason that drives most decisions like this, is really one of economics, that it ends up being cheaper because of economies of scale to have a big shared data center that's being used by lots of people at lots of different times than for everyone to try to run their own data center. And it's really interesting. I was at a conference on cloud computing recently, and there was an argument about whether having a big company run your system, like you pay to store your application or your service at Google or Microsoft or at Amazon or one of those, versus running it yourself, which was more secure. And the person who was speaking was somebody from one of those companies, and he basically said, listen, I can afford to have 200 system administrators. And because I have 200 system administrators, I can have 20 of them be experts in security. Okay? If you've only got one system administrator, that person is going to be a 10% expert in computer security. So who's going to be able to deploy a more secure service? Right? So there are those kinds of economy of scale arguments that come to play in this. And that's why one of the reasons this is taking off. It's also, if you're buying things in bulk, you can get them cheaper, you can set up the data centers more cheaply, and so on. Everyone, well, I won't say everyone, but broadband connection is getting, more and more ubiquitous. Everyone, or almost everyone, has it, at least, in developed countries. And so, certainly in those regions, it makes sense to. It's not a problem that the service is actually geographically separated from where where the users are. And then, there's some advantages that we'll see and that they talk about in the chapters that we had on the list for today about you can standardize on a particular hardware vendor and a hardware type. A lot of these companies build their own servers. We'll see a picture of that in a little bit. And you can standardize on a software stack, and so then that makes things easier as opposed to trying to manage lots of different hardware, lots of different software. Okay, so this is all economic. You guys are going to get to use a service called EC2, the Elastic Compute Cloud, which is run by Amazon Web Services. And Amazon was generous enough to give us a grant to give you guys accounts on Amazon on EC2. You still got to be careful with them. We'll talk about that when we get there. We're gonna be very careful about how much we spend because 300 people doing the wrong thing can be very expensive. What EC2 is it's basically a service where you go if you're not lucky enough to be in a class like this. You give them your credit card, and they allow you to rent resources. And the resources you can rent. There's storage, there's applications, there's all sorts of stuff. But the basic resource for EC2 is computers, okay? And this is just showing that you have a menu when you go to Amazon Web Services. There's a menu of machines you can get. So, there's kind of small, large, and extra large. And those kind of scale up in terms of, how many cores they have and how much memory they have and so on, how much disk they have. But then you might want to be doing more specialized things. So you might need, extra memory, so you can get these guys. Or you might be doing like some very detailed simulation that's very compute intensive. So you can, they have high CPU instances. And basically, this is the price that you pay per hour. Okay, so if you wanted to build a supercomputer with, say, I don't know, let's pick an easy one. 1,000, high memory double extra large systems, which as you can see are, what is that? 4 cores, terabyte of disk, 34 gigabytes of memory. So 1,000 of those, it would cost you $1,000 for an hour. And before this kind of cloud computing happened, there were only, there was a list of the top 500 fastest computers in the world called the Top 500, published every year. Only a few years ago, that thing you're renting for $1,000 an hour would have been on that list. So, tremendous way of sort of getting a bunch of resources, using them, and then letting go of them, okay? Yeah? Mm. Okay, so that's a somewhat advanced but great question, which is, hey, we're going to end up using Hadoop on this thing, which is this MapReduce system. A lot of you guys have already seen MapReduce in 61A. We're going to be talking about it again on Friday. Since Hadoop runs in standalone mode, why don't we just run it on our machines? And the answer is because we really want you to get the experience of using these cloud resources. And in fact, part of the next project is going to be get your system running on a certain number of nodes, measure the performance, and then scale it up to twice that many nodes and get the performance. So, if Amazon hadn't come through with this grant, then we very well may have done what you said. But, Amazon wants you guys to learn about cloud computing because they think in the long run that's good for them. So, they're willing to let us use it for free, and so we're going to take advantage of that. So, okay? The other thing I'll mention, which is a slightly off topic, but if you're business inclined, it's kind of interesting. There's another way to buy resources, particularly from these guys, which is they have what's called the spot market. Okay, and the spot market isn't fixed price. It's basically you go in and you put a bid. You say, I want this many resources at this time, and I'm willing to pay this much. And it's basically, like the stock market or something. If your bid's the best one, you get it. Okay? And so what that lets you do is basically you can think about, if you're less time sensitive about when you get your work done, maybe you can run your job at night, when it's at night in the U.S., and run it on some U.S. data center, and you'll be able to get the resources for much cheaper. Okay, and I'll show you why the spot market's interesting in a little bit, but it basically really gets it down to this utility where the cost of computing is like, it's just the way people bid for electricity and so on. It's just another utility. Yeah? Why are the numbers for memory so weird? Well, let's see. They're pretty weird. I don't have a good answer for you. I mean, I will say that the way this thing works, most of these systems are actually virtual. You don't actually get a box to yourself. So I think if you go to standard extra large, that is a box, but that's still kind of a weird number. Okay, but there's another thing going on here, which is virtualization, which is, if you buy a standard small machine, you rent that for an hour, you don't actually get a machine. You get a virtual machine, which is running on. So I think that's part of it too. Oh, you think it might be virtual? So it might actually be virtualization. Oh, that's interesting. Okay, so Professor Garcia is hypothesizing that this might actually be 2 gigabytes, but you lose 0.3 gigabytes to the virtualization. Oh, it's a good guess. Any other guesses? Maybe they bought discount memory and some of it doesn't work. Yeah. You think they chose it to make the cost come out even? That could be too, right? They made it half of, the mysteries of Amazon pricing isn't exactly what I wanted to go over. Yeah? That's what they guarantee you. They guarantee you that performance. Could you get more? I think in some cases they would let you, get more than that. But that's what you're guaranteed if they're fully if they're fully utilized, if they're fully busy, and their job is to keep everything fully busy. So, that's pretty much what you get. And there's other costs. There's costs for data transfer. There's costs for data storage. There's costs for running certain applications. I'm not showing any of that here. This is really just about the hardware, or the virtualized hardware. All right? But the key concept here is, before, if you wanted to have access to a 1,000-node computer, you had to build it. You had to go out, buy those 1,000 nodes, find a place to put them, whether it was in your own data center or you rented space in somebody else's data center. Okay? And that's a huge capital outlay, right? That's a huge amount of money to put up a 1,000-node server. Here, you need it for 2 hours, you rent it for 2 hours. That's the beauty of the approach. And that changes everything. That means any of us. That's why there's so many startup companies now that are able to put out, interesting applications without having to raise a lot of money, because they just rent things from a cloud provider, and then as their service gets more popular, they just rent a little more, and it works. So interesting stuff. Completely changes everything. So, okay, now that's kind of the economic side of the whole thing. This cloud computing, at least the way we talked about it here, is really about, how do I think about buying computing power? But what most of the chapters is about, what most of the chapter is about, if you look at them, is really something slightly different than that, which is this idea of a warehouse scale computing, okay? And it's the same thing. So, cloud computing is basically serving up warehouse scale computers, kind of by the slice, okay? So, but the authors of the book make it a point to say that, the important concept that they're trying to get across is, even though you might be running on a system that has 10,000 servers or 100,000 servers, you want to, as a user, to be able to think about that computer as a single computer. So just as if you would take a program and do what we talked about last time, the compile, assembly, link, load, right? And then that gets installed in the memory and you go off and you run it. You'd like to think about doing that same type of process, but instead of on that one machine that's sitting in front of you, have that happen on a huge a machine that's taking up a big part of a warehouse. Okay, so it's not just about having lots of machines, right? There's always been big data centers, at least for a long time, right? Where you have racks and racks of machines, and this rack is owned by this company, and this rack is owned by this company, and so on. This is saying something different. This is saying you have all those machines, but conceptually, to the programmer, to the debugger, to the developer, it looks like you could think about it as if it were, in some sense, a single machine, just a really big, fast one. Okay? So that's really what it's about. And so because of that, the hardware you get tends to be pretty similar. I mean, sometimes you'll get two different versions of a processor because they bought some new ones, but in general, the hardware tends to be pretty homogeneous. You tend to run big applications on them, like web search or serving video or your social networking or anything, right? Because that's why you need such a big machine, because you're doing these big things. And the key thing is, or another key thing is, you really need to make it very highly available, right? So, when one of these big data centers or big cloud providers goes down for more than just a little hiccup, it makes the news, okay? So basically you get, like an hour of downtime a year. That's your whole budget, okay? So if you think about what that is in terms of reliability, it's 99.999, 4 or 5 nines, to the right of the decimal point. Okay, it's really hard to do. We talked about in the first class when you're running a system with 10,000 disks, how often a disk fails, and the answer was like once an hour, right? So imagine trying to get that kind of reliability out of a system that's always got broken pieces. That's why it's hard. And then this is kind of at the very beginning of the book. They make this case here, which is important, which basically they say, the reason we wrote this book and the reason we're giving it away is that we want everyone to think about this class of system, these warehouse scale computers, the same way they would think about any other computer. So just as if you're a computer scientist and you're interested in studying, making processors go faster or making graphics processors go faster or something like that, it's just as valid to be thinking about how to build the software infrastructure and the deployment of these warehouse-scale computers. So it's a computer science problem. It's not an engineering problem. Or it's not just an engineering problem. Okay? All right. So, you know, what are the design goals for this? You got to have lots of parallelism, right? So if you remember Amdahl's law, if you have a task that only that has to run in serial, you could have as many machines as you want. You're going to get no benefit from adding new machines. Okay? So you have to have work that's parallelizable, and we're going to talk about the different ways that can happen, right? And it can be done by having multiple programs. It can be having a program that has multiple threads of control. It can be done by having, smart ways of splitting things up. But if you don't have parallelism, you can't take advantage of this. The other thing is, how do you take advantage of the scale, right? So these are huge, huge systems. That gives you a lot of benefits, like we've talked about in terms of economic benefits. But there are problems with it, too. One is dealing with the failures. Another is, no matter how big a company you are, you don't build that many massive data centers. So there's not really, so you do all the design for one, you don't necessarily get to carry that over to the next one or all of it over. And then the other thing is that in general, when you look at a picture, and I'm going to show a couple in a second, with lots and lots of hardware, you think, boy, that equipment must have been expensive. But the truth is, if you're not careful, the cost of owning that equipment can dominate the cost that you originally paid for the equipment. So it's all about maintenance and management and all that stuff. All right. So we've seen pictures like this before. I showed you Google's new data center in Finland. This is one that also Google, it turns out, that they built near the Hood River in Oregon. And again, why is it near the river? Well, there's cheap electrical power there. There's cooling there. And, cooling is a big deal for these things, right? But, if you were just driving by this thing, you wouldn't know whether it was a, factory or a warehouse or a data center. And that's actually the way they like it. So if you were to drive by here, you would not see a big billboard that said, "Welcome to Google's data center," right? Because they figure if you don't know that that's what it is, they don't want you to know, okay? Because there's no upside to you knowing that. Okay, what's cool is you look inside there, and I think I've showed you this before. The way people are deploying these things now is they're putting them in these containers, right? So the things you see driving, on the back of trucks when they come into the Oakland port and they load it up, it's full of stuff, to bring to Walmart. Same exact technology, except it's stuffed with servers, okay? And then all the cooling and all the stuff and all the networking you need to make the servers work, okay? All right, and what's good about these things is you could just keep adding on new ones. And as I think I told you at the beginning, a lot of times, a lot of new data centers have even gotten rid of the building part, and they just stack these things up, in a parking lot. Okay, and it just scales out. So it's kind of interesting. Okay, so let's look inside there. So what's the equipment look like? So the kind of the basic unit is a server, and the server consists of some number of chips, CPU chips or processor chips. Those chips each contain multiple cores. All right, there's also memory in there, some amount of DRAM. Here it says 16 gigabytes, and then some amount of disk. Okay, so each of these is kind of a complete unit, multiple processors, a bunch of memory, a bunch of disk. Okay, and it's on a rack. It's rackable. So then what you do at the next level of the hierarchy is you stack them up. Okay, so this is a rack. 40 to 80 of these, okay? And in the middle here is the switch, is the communication. So all of these guys, if you look in the back of this, it's just a big jungle of wires. And all of these server boxes are plugged into this switch, okay? And it's in the middle because that's kind of the cleanest place to put it, right? You take each of those racks, so there's 40 to 80 servers in a rack, and you organize those into arrays or clusters. And clusters consist of some number of racks. Here the example is 16 to 32. And there, the communication is in a separate switch, right? Because here the communication is in the rack. Okay, here you've got a separate switch that's handling the inter-rack communication. So if two servers need to talk to each other, within this rack, it just goes to this local switch. If something in this rack needs to talk to something in this rack, it goes through the cluster switch, okay? And so what that means is cluster switches need to be really, really fast. And in fact, they need to be about 10 times faster than what you'd find in one of these. You'd like them even better than that if you have that many racks. And because they have to be so much faster, they're much, much more expensive. So the number here is 10x faster, costs about 100 times. Yeah? Yeah, so we're going to talk about that just in a second. So that's exactly the right thought to be having. And if you're thinking about, is there anything I can get out of this lecture that would be at all helpful for the exam? That's exactly what it is. This is just a hierarchy. We've seen this before, right? We've just added more levels to it, okay? So I think that might actually, okay, there's just a picture of this stuff to show you it's real. Let me come back to your question and to finish up that question in a second. This is, Google is kind of pioneered the idea of making their own servers. So they assemble these themselves. And you can just see, it's got, I assume what's under here are the processor chips. It's got 2 disks. I don't know what the heck that is. And this is interesting. This is a battery, right? This is battery backup. So one of the big secrets that they had for years, that somehow they kept secret for like 5 years, was that, remember, reliability is key here, right? You only get an hour of downtime per year. So all of these systems have a big uninterruptible power supply, right? The UPS. Traditionally, the UPS was just a big box or a bunch of big boxes that sat in the data center, and when something bad happened to the power, they flipped on, and all the servers got power from there. The innovation here was just to put a small but individual UPS on every server, okay? And this turned out to save them all sorts of energy. I'll show you in a second, but it resulted in big energy savings and so on. So that's the view from the other side, and that's the power supply of the UPS right there, okay? You think on the other side? That's the battery. You think this is the power supply? Oh, look at that big cable. Okay, good. So power supply. Yeah. So power supply and then the battery. I'm a software guy. Okay. All right, cool. So, all right, now let's get to your question. So, didn't we just add stuff to our hierarchy? And the answer is absolutely no question about it. So now, remember all the stuff we talked about, right? You got your registers, level 1 cache, split between instruction and data. Level 2 cache, typically unified, right? You mix the instructions and the data in there. Level 3 cache, often shared among all the cores on a single die, right? And then DRAM, and then disk. Well, take that whole hierarchy, that becomes what we're calling here local, right? That's what's going on in one of those server boxes. But now we're going to extend that because, as was said, the next furthest thing away is another server that's on the same rack as me, right? Because if you remember that picture, all the servers on the same rack got to talk to a local switch, right? Then, if I can't find what I'm looking for in the local in the local rack, I might have to go to some other rack. That's got to go through that big shared switch, and that's going to take even longer, okay? So that principle that we had of hierarchies and things being, close and small and further away and bigger, it also holds here. Now, we're not going to use this the exact same way. We're not going to, if you remember in our processor cache, we would take something from memory. Well, we would look to see if it's in level 1. If it's not there, we'd look in level 2. If it's not there, we'd look in level 3. If it's not there, we'd get it from memory, and then we'd come back the other way. We'd put it in level 3, level 2, level 1, and we'd give it to the processor. Here, we're not going to do that, necessarily copying it all the way back up, but that principle of locality is still going to be a big deal here, okay? And arguably even a bigger deal than it was when everything was relatively close. So, just some numbers, in a rack, we have 80 servers. In an array of 30 racks, we have 2,400 servers. That's going to translate to about 20,000 cores. That's a pretty big parallel machine. You can see things about, how much memory. This is, I believe, 9 petabytes. Am I doing my math right? I think that's 9.6 petabytes. That's a lot of data. And then the interesting thing here is, if you look at the latency, right? Remember, there's two things we worry about in terms of performance. Latency is how long does it take to do something, and throughput is how much work can I get done in a unit of time. Okay, so latency is how long does it take me to do something. And what you can see here is going to the local disk is much, much more expensive in terms of microseconds than going to the memory of some other machine, even if it's not in my own local rack. Okay? So think about that when you're designing your software. If I can find something in memory on a machine that's across the other side of the room, that's going to be, 2 orders of magnitude cheaper than if I have to access it from my local disk. Okay? So that's going to tell you a lot about how you want to design your software. Okay? That's in terms of latency. Unfortunately, the relationship's a little different for bandwidth, right? So how many megabytes per second can I send to a device? And it turns out there, my bandwidth to the local disk is better than my bandwidth to memory, even in the same rack. Okay? So if I'm interested in sort of just getting one thing and I've got somebody waiting for it, I'm willing to go even across the room. If I'm trying to stream out a bunch of data, like you just uploaded your latest video to YouTube and I got to put it somewhere, I'd rather put it on my local disk than try to send it to even another server in the same rack. Okay? These are all the things that somebody's thinking about, and hopefully it'll be you guys, when they're designing their software for these systems. Okay, so the comment about, is there locality concerns here? Yeah, absolutely, and those are the numbers for them. Okay? So, now I got two other things I want to talk about, and then we'll wrap up. The first one is this idea of workload variation, okay? So, this is what's called the diurnal, the diurnal cycle, and this basically says, at midnight, the workload's pretty low, people start waking up, everyone's working really hard at noon, and then people start going home, and then, it goes back down, okay? Now, if you're building a data center or a warehouse-scale computer, okay, if you took the average utilization of this, it would be somewhere, around here, right? So, but unfortunately, you can't build your system to handle the average utilization, because that would mean every day, at the worst possible time, you'd be overloaded. So when you size your system, you have to size it for the peak usage, right? And so here, this is showing the peak usage is twice. So you have to build a system that's twice what your off-peak usage is, okay, in terms of capacity. And furthermore, that's probably not good enough, because every once in a while you have a spike, so you probably have to add another factor or two, right? So if you're not careful, there's going to be huge chunks of time when your resources are only being used like 10, 20%. Okay? And that makes this less economical, right? So the whole point of putting everything together in a warehouse-scale computer or a cloud computer is that by doing that, you can keep everything busy all the time. So that's one reason why Amazon has these spot instances, because what they want to do is they would rather sell you resources, right? During this period, they've got all these computers sitting idle. They'd rather sell you those for cheap than to just let them sit idle. So the people who really care about getting their work done at noon pay more. The people who are willing to wait till nighttime can pay less. Yeah?
They serve like one setup because if it's night at one place, it's going to be like day at the other place.
Yeah. So the question was, well, can't they fix this problem by, mixing workloads from different parts of the world in the same data center? And the answer is absolutely yes, they do that. But there's a couple problems with it. One is there's a lot of parts of the world where the usage is still pretty low. Okay, so certainly North America and Europe dominate currently. And then the second problem is it's a latency problem again. If every request you make to the web goes to some web server, in Japan or something, you're going to notice that in latency, because it's minimum 100 milliseconds each way, and probably a lot more than that. So just for locality, you have to be careful. Just for response time, you have to keep the important stuff near where the people are. But in general, absolutely, people try to play the trick of moving work around data centers to solve this problem. Any other questions about this? Okay, yeah, 2x. Okay, so, we've kind of talked about all these. When you're writing your software for your warehouse scale computer, you really got to worry about where things are placed in the hierarchy, because that's going to impact performance. You got to be able to handle a situation where at every time part of your system is broken, and you still get the good performance. You got to be able to scale up and down gracefully. So when we start Project 2, the Amazon people asked me to send them an email, 3 or 4 days before, warning them, just so that they know. I mean, not that you guys are going to, take over. You better not, because we don't have that much. They didn't give us that much of a grant. But they want to know, because they need to be able to scale up and down. And the fact that your memory hierarchy is even bigger than the one we were already talking about, and you have these failure problems and so on, means that there's a lot of interesting challenges for developing these kind of computers. And in fact, if you come over to our lab in Soda Hall, the AMP lab, this is a lot of what we do, is figure out how to build the software to make these things run more efficiently, faster, and let you do more with them. So it's a really interesting problem, not solved yet, but certainly these things work. All right, so the last thing I want to talk about quickly is energy use and power. So this is an interesting graph that I think comes from that paper, where basically this is the percentage of the peak power that a server uses. It's broken down into whether it's being used by the CPU or the memory or the disk or other stuff, okay, where other stuff is communication and things like that. And it basically goes from the system being totally idle, so basically it's not doing any work, to the system running at 100% capacity, okay? And the scary thing that you see here is that even in the idle state, you're using almost half the cost of the power. So there's another project in our department called Local, which is focused on energy usage in data centers and beyond. And their motto is, what's their motto? You should be able to do nothing well. Right? So doing nothing well is their motto. And what they mean by that is this server's doing nothing. It's idle. It's not doing anything, but yet it's using 50% of its power. Okay? That's bad. What you'd like is if it's not doing anything, that it's basically using no power. Okay? But that's not the state of the art. So, when you're idle using half the power, by the time you get up to 50% busy, you're already using 90% of your power. Okay? So it's expensive. All right? So that's the problem. And the other thing is, for that reason I just showed you with that diurnal curve, most servers on average are utilized, 10 to 50%. So that's a problem. So the goal is this idea of energy proportionality. So in the readings, we had 3 things to read. One was the introduction, what's a warehouse scale computer. 2 was a little more detail on the architecture, all this stuff about racks and arrays and stuff like that. And then there was a subsection of, I think it was chapter 5. That's all about power, and that's because, as we talked about at the beginning of class, it's a big deal, right? Google's proud of the fact that that each one of you in this room only burns, a 60-watt bulb for 3 hours for them, because if they weren't careful, it'd be a lot worse than that, But so that's the idea. So just a little terminology. Don't get too hung up on this, but the overall energy efficiency, which is the amount of computational work that gets done divided by how much energy gets used. Okay, that makes sense. So, the more work I can do for the same amount of energy, the more efficient I am in terms of energy. That's good. But the one that's a little more interesting is this idea of power usage effectiveness, or PUE. And what that is slightly different. I've got this big building, this data center, and it uses a certain amount of power. You divide that by the amount of power that's actually used by the computers. So computers and networks, everything else is overhead. Okay? And what you want is that ratio to be as close to 1 as possible, so that you're only paying the power for the computers. Okay? But it turns out that's not what you get right now. In general, half the power in the data center goes to stuff other than the computers. Okay? And where does it go? This is one breakdown that, again, I think came from those from that chapter. Some of it goes to the UPS, some of it goes to all this blue stuff is conditioning, air conditioning, and the things you have to do to make air conditioners work at that big of a scale. Lighting is 1%. Why? Because there's no lights, right? It's just they're sitting in these containers, right? But in this picture, the IT equipment is only 30%, right? So the PUE is like 3 here, okay? So it's bad. So Google, again, they're sort of the people who publish the most about this, and they're the authors of the reading for this class, for this lecture, which is why we talk about them a lot. But they go through a list of things that they do to get, they claim in one of their big data centers they're at 1.25. And remember, 1's as good as it can be. Okay, so there's a 25% overhead for everything that's not computing. And the way they do it is, and they discuss this in the reading, is they're really careful about how air moves in the data center or actually within a container. So, cold air goes here, hot air goes here. They make sure that happens. They found out, for years, people kept data centers at 65 degrees. So you would go into a data center, and it would be cold. And after a bunch of studies, people realized, you know what, there's actually no reason to do that. No one had ever really studied, or at least with modern computers, why you need to keep the data center at 65 degrees. Just everybody did it. And so they find that data centers, the computers work perfectly well and last a long time, even if the data center is as hot as 81 degrees. So turn down the air conditioning. That's fine. They try to use cooling that's free. So they, that's why they built a data center in Finland. Cooling's pretty free in Finland. This trick we talked about, where they put a battery on each server, turns out to get them, another 9% of energy efficiency. The other thing they mention, and this is why they released those numbers, is that, they want to measure how good they're doing with power usage, and then they want to publish that, and then they want to try to improve it, and they want to have a competition with other data centers to try to get them to improve it as well. Okay? So that's the story on power. So, this is the wrap-up, and again, we're not going to have any of this on the exam. Quick question?
Oh, yeah, I was just wondering, because this technology is relatively new,
Yep.
I can imagine there are a lot of companies that are doing these things.
Yeah.
Say, chemical companies who
Yep.
that just might not have people in companies who know about it.
Right. Right.
How is Amazon and Google trying to compete?
Okay, so the question is, there's probably a lot of companies that aren't aware of this technology existing, and how are the cloud companies and these warehouse-scale computing companies fixing that? And the answer is they are making a lot of noise. They are advertising. And if you go to any sort of conference for IT people, this is like the #1 topic that people talk about. All right, so just to wrap up, the reason we're talking about this is parallelism. That's the big idea. Now you're allowed to forget about everything we talked about until Friday. So good luck getting ready for the exam, and we'll see you Thursday night. Don't forget, go to the right place.